All right, here we go. So, how do you name ionic compounds? But first, what are they? Okay, so what is it? Before we start with naming, what is an ionic compound and ionic? Ionic compounds are formed when a metal transfers an electron, or more than one electron, put an S there, to a nonmetal. Electron or electrons. It doesn't have to be just one, it could be many. It looks like this. For sodium, its configuration is 1s2, 2s2, 2p6, 3s1. And it has one valence electron. And it likes to pair up with chlorine, which is 1s2, 2s2, 2p6, 3s2, 3p5. And it has 7 valence electrons. Should be good right now. No? Yeah, for this unit, there's not a lot of PowerPoints. It's mostly things that I write and skills that I expect you to be able to have. So how does this work? How does a metal pair with a nonmetal to make an ionic compound? Well, what's the mentioned number for valence electrons? Everyone wants to have how many? 8, correct. And so if sodium loses this guy right here, it would be left with this for its valence electrons, which are 8. 2 plus 6 is 8. And if this valence electron is given to chlorine, then it would have 2 plus 5 plus the one more it's getting, which would be 8. And that's how an ionic compound is formed. And when that happens, sodium becomes positive and chlorine becomes negative. And you might remember that positives and negatives opposites attract each other. And so what you get is you form NaCl, which is table salt. Yum yum. And this happens pretty commonly. Okay, they can, by giving away, so sodium wants to get rid of an electron, chlorine would love to get one, so they can solve the problem together. If chlorine or sodium gives its electron to chlorine or transfers it, then what happens is you get the positive and negative charge. There's a huge attraction there, and they form a very strong bond. Okay? Sodium and chlorine are just stand-ins for any metal or nonmetal. All the metals will lose electrons. And when that happens, they become positively charged. And when you're a positively charged particle, you're called a cation. So positively charged particle is called a cation. And it looks like cation, but it's pronounced cation. And then all nonmetals will gain electrons. Oopsies, I'll write it out. And become negatively charged. And those are known as anions. Now noise doesn't work there. Anyway, looks like anions, but it's pronounced anions. Every ionic compound is made up of cations and anions. Positive charge and negative charge. We actually know the charges of all the elements, I'll come back to that in a second, based on their position in the periodic table. And you're going to want to write on your periodic table, just like I do on this one. Everything here in this first column, all those have how many valence electrons? 1. They'd love to get rid of that one valence electron, and when they do, what's their charge? plus 1. So right there you can write plus 1. They will always form plus 1 ions, plus 1 cations. Second column has 2 valence electrons. They'd love to get rid of both of them. When they do, their charge becomes plus 2. Oopsies. Just go away. Now, the transition metals here, they have more than one possible charge because the d orbitals are complicated, so we're not going to worry about them for right now. We're going to come back to them at the end of the hour, though. So let's skip to here. They have 3 valence electrons in this column that we'd love to get rid of, so our charge becomes plus 3 if we lose all of them. The tipping point is carbon, because the magic number is 8. Carbon has 4, which means it could just as easily lose 4 or gain 4. And so they often form charges either plus 4 or minus 4. You won't really need to know which one, but we'll talk about it later. Now we're closer to 8. So nitrogen would love to gain 3 more. It has 5 valence electrons. When it gains 3, it becomes a negative 3 charge. Oxygen, that whole column or group, becomes a negative 2 charge because it gains 2. Fluorine is 1 away, it gains 1 electron, becomes a negative 1 charge. How about the noble gases? What charges do they get?
No.
They don't form compounds because they already have 8 valence electrons, so theirs is 0. So going across, plus 1, plus 2, skip these for now, we'll talk about them later. Plus 3, plus or minus 4, minus 3, minus 2, minus 1, and no charge for those. So we know them pretty reliably. And bless you, we're going to come back to them in just a minute. Let's talk about properties of ionic compounds, because there are many properties that they have. And we're going to compare these properties to covalent compounds when we start them later this week. So, properties of ionic compounds. I just told you they're made of what always? At least one something and one something else. Yeah, they have electrons that are transferred, but what groups in the periodic table make up ionic compounds? Yeah, metal and nonmetal, right? When a metal transfers to a nonmetal. So always metal to nonmetal, or always metal and nonmetal. We didn't say this, but I think we remember the metal side is everything left of the stair-step line, so all of this is all metals up here, up there, and down there. And all the nonmetals are the very small right-hand corner right here. That's the nonmetals. So they're always made of metal and nonmetal. And then salt is actually a pretty good representative ionic compound. Okay, so they're all solids at room temperature. Have you ever tried melting salt on your stove? It won't happen because salt has a really high melting point. All ionic compounds do. So they have high melting points. They're almost always crystal structures. Usually white, but they don't have to be, but salt's a pretty good example. They also dissolve really well in water. And when they do that, they conduct electricity. Why do they conduct electricity?
Because you said so.
Yeah, but why? Because this is positive and negative. That's dissolved in the water now, and so that water will conduct electricity. Okay, so that's most ionic compounds are like that. They're metal and non-metal. They're solids at room temp. They have high melting points. They have crystal structures. They dissolve in water and conduct electricity when they do so. Another common household chemical that we eat looks a lot like salt. What is it? Sugar, right? It's small white crystal, solid room temp. But actually, sugar is not an ionic compound. Sugar will not won't conduct electricity in water. And it has a really low melting point. You can melt sugar on your stove to make caramel. Is that how you say it? Caramel. I say caramel. Is that okay?
It's caramel.
It's not really.
No, it's caramel.
No, like there is no one correct pronunciation. Also, when you say caramel, you're totally ignoring the fact that there's an A between the R and the N. Think about that.
But it's caramel.
Yeah, but think about what you're ignoring. Right?
No.
Like when you say caramel, you're totally ignoring a letter.
You're not.
Anyway, here we go.
You just don't hear it.
Yeah, that's totally a silent A. Yeah, for sure. right, how do you name them?
The person says the thing, you just don't hear him say it.
Gotcha. All right, now you know a little bit about what an ionic compound is. How do you name them? Remember, there's still a metal and a non-metal, always. The naming rule is actually pretty straightforward. The first rule is that you name the metal. Regular name off the periodic table, no change. The way they're listed is always metal first and then non-metal second. So it's always the first element you name. Then you give the non-metal an IDE ending. And if there's numbers in the formula, you get to ignore them. You won't need them to name. Here are some examples. Start with the one that we already kind of know. When you name this, you see it's got two pieces, a metal and a non-metal. Name the metal always, which is sodium. And the non-metal is chlorine, but you want to change it to an ID ending, so you call it what? Chloride. You just named your first compound, sodium chloride.
Yeah.
Yay. If there's numbers, you ignore them. You still follow the same rules. You still name the first one and give the second one an ID ending. So the first element here is what? Magnesium. Iodine becomes what? Iodide. I don't know. Some of them get weird. Specifically, nitrogen, oxygen, phosphorus, and sulfur are nitride, oxide, phosphide, and sulfide. So those ones get a little strange. One more? I had a good one last hour. Oh yeah. Try to name that. Got it? The A3N2, ignore the 3 and the 2. Still name the first one is barium. And the second one is nitrogen, becomes nitride, N-I-T-R-I-D-E. How many of you have barium nitride? Okay, naming is the easy part. Writing formulas is more challenging. So how do you do it? How do you write formulas for ionic compounds? Question mark? The thing you need to remember that the overall charge of any ionic compound is 0. What's happening, I guess on a picture level, is if I had, let's say, one sodium which is positive 1 and one chlorine which is negative 1, you can see very clearly that they would just cancel each other out, right? And the formula is NaCl. What's really going on is that sodium has 1 valence electron represented by that dot. Chlorine has 7 represented by these 7 dots. And it's got an empty spot. We'd love to have 8. So sodium gives its valence electron to chlorine, and they form a compound because this becomes +1 and this becomes -1. That's how the compound works. If there's more than one, like let's say magnesium, which is +2, and chlorine, which is -1, well, magnesium has 2 valence electrons, and chlorine only has 1 spot, right, for valence electrons. One of the electrons goes right there. But guess what? Now I need another chlorine for the extra spot. So I still have to give away 1 valence electron, so that valence electron goes right there. How many chlorines did I use? 2 of them, right? And I needed 1 magnesium, so the formula is MgCl2. That's one way to think about it. Another way is to say if the whole thing is neutral, if this is +2, how many of these do I need to cancel it out? I would need 2 of them because that would be -2, and -2 cancels out +2. So the formula is MgCl2. There's actually an easier way to write the formula, but that's what's happening on an atomic level, is that I want to get rid of 2 valence electrons. Chlorine's my only option. It only has 1 spot. So I'm going to use another chlorine down here to get rid of the second valence electron. Or magnesium's +2, chlorine's -1. I need 2 of these to cancel out one of those, or to pair up with every one of those. But don't worry, there's a simpler way to do it, called the crisscross method.
Sounds fun.
It's so fun. It's got 2 steps. The first step is to write out the ions of the charge with the charges. Second step is to crisscross. Okay, that's it, we're done. Here's your homework. So easy, right? Let me show you what that is. Okay, strontium phosphide. The first step here is to write out the ions of the charges. So look in your periodic tables right now. Find strontium, it's in metal, which means it's on the left side. It's in the first 2 columns. And write its charge out just like this. Strontium, and what's its charge?
+2.
+2, it's in the second column, just like so. Do the same thing for nitrogen. Find nitrogen on the right side. Oh, sorry, it's phosphorus. Phosphorus on the right side. What's its charge? -3 is correct. Okay, before we do crisscross, let me just show you. The whole thing has to be neutral. So if this is +2 and this is -3, I need to get them both to a common multiple of 2 and 3, which would be what number? It's the lowest. 6 is correct, right? So how many of these would I need to get to +6? 3 of them. How many of these would I need to get to -6? 2 of them, and then they would cancel out and the charge would be done. Okay, that's what's happening. Here's the easy workaround to think about what I just said. Is just to take this 3 and put it right there, and take that 2 and put it right there, and ignore the charges because they go away, and the formula is SR3P2, which is the same thing we just said. We need 3 of these to get to +6, we need 2 of these to get to -6, and then it ends up canceling each other out. That's a formula. Letters and subscripts, that's it. This is the work. You're not going to need to do this, every one of you, every single time. As a matter of fact, I can say this to you, probably there's 10 of you right now who won't ever do this, because you can do this part in your head, you can visualize it. But if you can't, then you follow the steps, write it out, and make the X, and that will help you. If you can, great, then just write the formula, that's it, that's all I need to see. This is just the work for you to show. A formula is not where you try to get lazy and smush this into one thing, where you write like SR, I don't know how lazy you can get. Like write big numbers, like a 3 there and a P. No, that's not a formula. Or you're trying to like do it all in once, and you write +3 and +2 and -3, and then you like write it down here, and then you cross them off. That's not right either. That's not good. Okay. Don't smush these 2 things into one thing. Your formula just has letters and subscripts. That's all. Don't try to make it something it's not. Don't try to be lazy with this. Either write this out or do it in your head, or that's it. And then write the actual answer. Questions about what a formula is? What it represents is literally in this, it's not technically a molecule, we'll learn about it later, but in this molecule, there are 3 strontiums for every 2 phosphoruses. That's literally all it represents. Okay? Did I use so many S's there? Want to try one?
A little.
Oh, there's some other things you should know. 1, don't write 1s. You don't need them. Also, like numbers cancel out. So like if one of them was +2 and the other one was -2, you don't write 2 and 2, you just cancel and get rid of them. Okay, bearing that in mind, write out the formula for magnesium iodide. Write the charges out, then cross them, either on paper or in your brain. Magnesium is +2. Iodine, which is working backwards from iodide, is -1. 1 goes there, but you don't write it. 2 goes there, and you get MgI2, just like that. How many of you had that? Super duper. If it's the same charge, just to show you really quickly what I was talking about with like numbers, that would be like barium oxide. Barium is +2. Oxygen is -2. No need to crisscross there. Just recognize that +2 and -2 cancel each other out. So the formula is just BaO. BaO. Questions on writing the formulas at all? Okay, let's make it more complicated then. Right?
Long recording.
Isn't it? We're doing good. I'm not even done. I'm not even close yet. Before class, Zach was asking me, he was like, what about the transition metals? And I was like, hold on there, bud. Let's talk about this at the end. And then he had all these questions about all the documents I shared with you guys this weekend. It's like, you had a really boring weekend. Why are you worried about chemistry so much? Got it. All right. The problem is that transition metals, which are these right here in the square, and some of these actually as well, the problem is that they have more than one possibility. They're not just always +1 and always +2. And that's because they involve d orbitals, and the d orbitals are more complicated than s or p orbitals. And electrons can live there or go other places. There's not just one configuration that works for them. So sometimes they're +2, sometimes they're +3, sometimes they're +1. Some of them are, there's some exceptions that are constant, but they can have different charges. And you don't need to memorize the charges. Like, you don't need to know that iron is always +2 or +3. You don't need to know that copper is always +1 or +2. But you do need to know that all of these have more than one possibility. So how do you account for that? I'll show you how. First is you need to remember that the transition metals are that having more than one charge is called multivalent. So transition metals are multivalent, which means they have more than one possible charge. So the easiest way to do it is when you're going from the name to the formula. In that case, a Roman numeral is used. To indicate the charge in the transition metal. And that's actually helpful to you. So, for example, if I told you that I want you to write the formula for vanadium 2 chloride, that 2 is the charge on vanadium. You still follow the same rules. You still write the ions, then crisscross them. But this 2 is the charge on vanadium. So it's there to help you when you're writing the formulas. The 2 has to be given to you. Okay? Vanadium has a whole bunch of possibilities for charges. So the person who wrote this is telling you that the charge is 2, not 3 or 4 or anything else. And even if it's a 1, the 1 is written. Chlorine, we do know. You can look that up. It's a negative 1. It's not a transition metal, so we know it's charged all the time. Always negative 1. Then you crisscross. 2 goes there, 1 goes there, VCl2. That's it. Yes, sir?
Are transition metals always positive?
Yes. All the metals are always positive, so there will always be positive Roman numeral. Good question. Want to try one? How are your Roman numerals? Do you know what V means? They're really not going to go much higher than 7. But V does mean 5. So go ahead and write the formula for manganese 5-phosphide. Manganese 5-phosphide. Again, follow the rules. Write the charges out first. Manganese is Mn. The 5 is the plus 5. That's what that means. Phosphide is phosphorus. You can look it up. It's got a negative 3 charge. You still crisscross. Take the 3 and put it there. Take the 5 and put it over there. You get Mn3P5. How many of you had Mn3P5? Hey, super. Great. Okay. Proud of you.
Thanks.
Formula to name is a whole different ballgame. So we'll start easy. Okay, when you write formulas to name, the first job is to say, I guess to think of the basic name, right? This would be iron chloride, and that's a great start. But how do I know you're talking about this iron chloride and not this one? That's where you need Roman numerals, okay? That's why you need them. Or you just say, oh, iron's right here, so let me just write its charge. Oh, wait, I don't know its charge because it's in the middle. That indicates that you need to use a Roman numeral when you write this out. So one surefire way to do it. You don't know what this is. You'll never know if it's a Roman numeral. But you will know what this is, right? You can look that up. What's the charge on chlorine? Look at it right now. Chlorine's the second to last column.
Negative.
Charge is -1. How many chlorines are there? 3. What's 3 times -1?
-3.
N equals -3. So like if you sort of divide this in half in your brain, this side is -3. The whole thing overall has to be what? What's the charge in any compound overall? 0. Okay, so if I want to cancel out this -3, what does this side have to be?
3.
+3 to cancel it out, right? And iron's the only thing there, so we call it iron 3 chloride. That's it, iron 3 chloride. So you won't know the first one, but you will know the second one, and you work backwards from there to figure it out. Want to try one? What if it's more challenging? Like, hold on. Give me a second. Just making it up. Good one. What's RH? Rhodium. Great. This is a great start. Rhodium oxide, we can get that far. That's good. Okay, but it needs a it needs a Roman numeral because it's a transition metal, and I have no idea what the rhodium charges could be. As a matter of fact, I'm not even sure if this could be this one, but that's okay. So how do you do it? Here's how. We don't know, but we do know this. Oxygen is what? What's the charge on oxygen? -2. How many of them are there? 5. What's that equal? -10. So this half is -10. And again, you can just do that part, sort of in your brain, right? The negative half is -10. So this half has to be +10. But there's a trick. Because how many rhodiums do I have? 2. So to get to +10, each one has to be worth what? 5, right? Or you can sort of divide 10 divided by 2. But the total has to be 5. So each one, the total has to be 10. So each one has to be worth 5. So we call it rhodium 5 oxide. That's the most challenging kind of you'd see. We have to like work backwards and then sort of divide at the end then. What? Yeah. Okay.
Can't you just like crisscross it?
Great. So today you can. I didn't teach you that, but you certainly could. You picked it up. You can reverse crisscross it, right? In that case it works. In this case that works as well. But that only works sometimes. And tomorrow you'll find out why. But today you can reverse crisscross to your heart's content. Sure. Yep. But it won't work tomorrow. And it won't work if they were the same. So if I gave you one that was like, well, let's say it was here, copper and oxygen. Okay, that won't work because what's the charge on oxygen? -2, right? And there's no 2 there to go backwards. So, and this has to be -2 and this has to be +2. So it doesn't work all the time, but it works sometimes. Yeah. Yeah, if they're the same, it won't work. Great question. Good, nice pickup. There are a handful of transition metals, the last thing I'll say to you, that are exceptions. They don't have more than one charge. They only have one charge. And I'm going to tell you what they are. And they don't need Roman numerals. So exceptions, transition metals that do not need a Roman numeral. Got kind of wordy. Oh well. Like, there's got to be an easier way to say that, but whatever. Some transition metals only have one charge, and they don't need a Roman numeral. That's what I should have said, but I didn't. I guess I kind of did. Here they are. Silver is always +1. Zinc is always +2. And cadmium is always +2 as well. Those are 3 that are, there are others, but those are the 3 most common that you won't need a Roman numeral for. Silver is always +1, zinc is always +2, cadmium is always +2 as well. Make a little, like that, triangle of death. Give me a triangle of exceptions. This whole chapter is exceptions, but that's kind of the start of it. Should I have some sort of closing sentiment? Yeah. In closing, this is how you name and write formulas for ionic compounds, including transition metals.